Hello, everyone. We're just giving folks a second here to join. Thank you so much for coming to our webinar today. Um, we're just going to give folks a couple of minutes to jump on. In the Zoom era, as we all know, it takes a few minutes for people to go from one digital room to another. This is the best digital room to be in, obviously, but it always takes a bit of time. So today we're going to be talking about a new report that we've just launched at the 2035 initiative. It's called A Clean Heat Climate Opportunity, a roadmap for electrifying low and medium temperature industrial heat. Wow, what does that mean? Well, we're going to tell you all about it, and I'm sure you're going to feel as excited about electrifying low and medium temperature process heat as we are. I will be co-presenting with my colleague, Dr. Eric Masanet, and we will also be joined by Senator Sheldon Whitehouse and Senator Martin Heinrich. So what are we doing today? Well, we're going to begin by welcoming everyone, doing some introductions to the folks. Then we're going to do a quick overview of the report so that everybody gets the sort of 101 of what our findings are. We'll have the senators make some remarks for 10 minutes each. And then Eric and I will walk through the report findings in detail. Um, we'll then have time for a Q&A on the report and then any closing remarks. So throughout this conversation, if you have questions you'd like to ask, feel free to hold them and you'll have an opportunity to ask them when we get to the Q&A near the end. So with that, I want to introduce everyone who's here today. My colleague, Dr. Eric Massanet, is an engineer. He's also a professor and the Mellenchamp Chair of Sustainability Science and Emerging Technologies, and he and I were the principal investigators on this report. I'm Dr. Leah Stokes, and I'm the Anton Bonk Associate Professor of Environmental Politics at UCSB. And we're very lucky today to be joined by Senator Sheldon Whitehouse, the U.S. Senator for Rhode Island and the ranking member on the Senate Environment and Public Works Committee, and Senator Martin Heinrich from New Mexico and the ranking member on the Energy and Natural Resources Committee. So these are really the people in DC who are leading the charge on making sure that we continue to make progress on our industrial emissions. So we feel really honored to have them both here today. Before I have them jump in and give you sort of 101 of what we find in the report, I just wanted to tell you what we're doing here at the 2035 initiative. So this is a Think and Do Tank at the UC Santa Barbara campus, where we are trying to make near-term progress on the climate problem. That's why we're called the 2035 initiative, and we're not the Project 2025. Some people sometimes get that confused. If only we had that much influence. So the idea here is to be combining engineers and modelers like Eric with policy analysts and political scientists to make high impact research that can help influence state policy and hopefully in the future federal policy as well, so that we can make progress in the next 10 years. Before I hand it over to Senator Sheldon Whitehouse, I just want to walk you through the key findings from our report. This report took us 18 months to do. It involved a very large team of engineers and policy analysts, and we went piece by piece through the food and beverage, pulp and paper, and chemical sectors, and really built out models of how these industries operate in the real world. And what we show is that low and medium temperature process heat electrification is possible today with the technologies that we have that are off the shelf, and that it can cut both climate pollution and create major public health benefits. So on the climate pollution front, we're talking about a thousand million metric tons, which is a gigaton of CO2 in terms of reduction by 2050. That is a big number for those who aren't in the gigaton trade. We also find very significant public health benefits. So we're talking about the order of 288 to 475 billion with a B dollars in public health benefits. These are things like fewer asthma attacks, fewer visits to the ER, and longer lives, because we know that pollution in our communities from these factories is affecting people. Throughout this report, we also look at energy efficiency upgrades that we can do to reduce overall primary steam production. And that's really a win-win because it reduces the costs. And we show that already in many states and some specific subsectors, electrification is cost competitive today. And even in places where it's not, Primary heat is not a big input into manufacturing, meaning that, for example, if you electrified a milk processing plant, a pasteurization plant, and it doubled your energy costs through electrification, that would still only add 1 cent to a gallon of milk. So we can do this. We can make progress today with the technologies we have, even with the cost as it is. And of course, policy support, whether in a future federal moment or at a state level, can really make this accelerate and drive faster and more affordable electrification. So with that, I'm going to turn it over to Senator Sheldon Whitehouse to give about 10 minutes of remarks, and then he'll pass it back to me, and then I will pass it over to Senator Martin Heinrich. So thank you so much for being here with us today, Senator Whitehouse, and I'll let you take it away.
Thank you, Leah. It's great to be with you, and thank you for your work on industrial decarbonization, which is a huge part of our climate solution. I'll touch on three things, but I want to open by saying how glad I am to be on this program with Martin Heinrich. Martin and I are the two ranking members, him on energy, me on public works. We're working on permitting reform, which I'll get to later. And he and I have been working on climate issues together as part of a little Senate climate team for quite a while now. And he's quite outstanding, as you'll see in his remarks. The three things I want to touch on first is CBAM, the Carbon Border Adjustment Mechanism in the European Union. If you track the Potsdam Institute's work, they've done a review of like 1,200 different climate scenarios that were generated for the IPCC process over time. And out of those 1,200 different climate scenarios, there are 11 left. 11 out of 1,200 left that get us on a pathway to climate safety. All the others are exits we drove by a long time ago, and they just aren't available to us any longer. So it is now essential to climate safety that we look at what those 11 different scenarios show, and all of them require a price on carbon. The pollute for free business model of the fossil fuel industry is lethal to our chances at climate safety. In addition to being morally wrong and economically wrong and environmentally wrong, it also is a dead end and a prescription for climate failure. So we really have to focus on trying to support and expand the CBAM. The UK looks like it's planning to join. Australia, I hope that the Prime Minister of Canada, Mark Carney, who knows this issue well, would include Canada when the UK and Australia are moving. And who knows, even Claudia Sheinbaum down in Mexico could get into this. She was an IPCC scientist in an earlier life too. So that to me is a prime focus for us. And it's also a prime driver of industrial decarbonization because it actually does put a price on carbon. It actually rewards people who go clean and assigns the negative externalities of fossil fuel to the fossil fuel projects that should have those negative externalities attached. So at all costs, the CBAM is our last lifeboat. It must be protected, and with any luck, actually expanded to include those other economies. Interestingly, there's even a bipartisan working group on a carbon tariff in the US Senate, but it's still, we don't have a bipartisan bill yet. So that's the first topic I want to raise. The second is permitting reform. If we want to bring the type of electricity to the industrial sector that it's going to need, particularly as you throw in AI data centers and crypto and all of that, we're going to need to improve the grid. And that's going to require permitting reform. And Martin and I are both working on that from our two different committee positions. All I'll say at this time is that the standard that I'm looking at here is that it has to be net emissions reducing. And I think we can easily do that because there's enormous economic and business pressure behind the clean energy stuff that is stacked up behind the grid because of grid problems. And the stuff that the fossil fuel industry wants to develop doesn't really have a market. They want to do it because they want to do it, but the world markets are saying, no, we're not interested. And there are all sorts of leaseholds that aren't being taken up and all of that. So I think we'll be able to show a very strong net emissions advantage, even with what Republicans would consider a balanced bill. We're also using it to tell the Republicans that if they want to get a big bipartisan permitting reform bill done, they're going to have to clean up the Trump administration's behavior. because I can't take a bipartisan bill and turn it over to an administration that's behaving the way this administration is behaving. My caucus won't let me. I don't want to do that. It would be foolish and wrong. And we're getting almost no pushback from Republicans on that. They basically agree with that proposition that the executive branch should execute the law faithfully, and that includes even the parts that they don't particularly like or that the fossil fuel industry doesn't particularly like. But we really need to get those electrons out there, and permitting reform will get lots of electrons out there. One point that I like to make here is about clean energy costs. I think this is always important because the big lie of the fossil fuel industry these days is that clean energy is a luxury we can't afford. And the fact of the matter is, if you go to the easiest way to prove this is to go to any of the ISOs, any of the grid operators' generation stacks, and look at the order in which they call up plants to be brought online to meet demand. It's always the nukes first, because they're cheap and constant. Once they're built, they're just running all the time. And then it's solar, and then it's wind, and then it's fossil fuel. They're the more expensive ones. And when you look at what Trump is doing to try to discourage clean energy and, in effect, ban clean energy, he's removing from the grid the lower cost providers. And that drives, to meet demand, drives the grid further up the fossil fuel stack. So that means that a fossil fuel plant that would otherwise not be running at all and not be making money because it's too expensive and too polluting, suddenly gets called up because of what Trump did to clean energy. So it's a direct transfer of money from customers' pockets to his big fossil fuel donors. And I think people need to understand that there's method behind the madness of driving up electric consumers' prices. And they're very deliberately engaged in that. I'll close with one final point. You know, the Trump administration runs around lying about the cost of clean energy everywhere it can. So when we had litigation over the offshore wind project in Rhode Island, we actually put the challenge in our pleading. We alleged in a court pleading tens of millions of dollars, depending on how long you extend the period, hundreds of millions of dollars in savings to consumers from this project. Now, that's different than just lying out in the open world. You don't have to come into a court environment. And truth-telling is more important in a court environment. And how did the Trump administration answer that? Not a word of contest to that. So whether you're looking at the clean energy, at the generation stack, or whether you're looking at things that must be said under oath, we've got a good opportunity to straighten out the fact that when you do industrial decarbonization, you almost certainly lower the prices for output at the end because the clean energy is almost always going to be cheaper. So thanks for having me on. CBAM, permitting reform with net emissions reduction, and don't buy the lie that clean energy is an expensive luxury. It's actually the cheaper product.
Well, thank you so much, Senator Whitehouse. You are always such an amazing champion for the truth and for climate progress, and we need that in this moment because I don't think we have as many champions for either of those topics as we had a few years ago.
Well, you got another one coming up next.
Yes, exactly.
Thank you, Sheldon.
So with that, I want to turn it over to Senator Martin Heinrich, who is also an engineer by training, so he understands how all these systems work in detail. So with that, why don't you take it away, Senator Heinrich?
Thank you, Leah. I really appreciate you allowing me to share a few thoughts this morning. And when I was thinking about industrial decarbonization and the pieces and parts there, I also started to think about like the kind of family that I grew up in this country, when we really believed in our nation to do big things, to build big things, to lead the world in manufacturing. My mom actually worked in a factory when I was a kid that made wheels for the auto industry. My dad was skilled labor. He was an IBEW lineman. And you know, we spent a lot of years figuring out how to decarbonize the generation sector. And we've made an enormous amount of progress when you think about that. And now we need to make that same kind of progress on these very heat intensive industrial processes. but we're America. We can do that. This is about chemistry and electrification and heat management and heat transfer, all things we've led the world in utilizing over the course of this nation's history. And so if you look at the power that's coming onto the grid right now, and Senator Whitehouse kind of alluded to this, the vast majority of it is now clean because clean is the cheapest power. And so we have an administration that is throttling back on all the cheap electrons that are trying to get added to the grid right now. And we need all of those, not only for industrial decarbonization, but also for the incredible increases in demand we're seeing. And so as part of this bigger conversation that Senator Whitehouse and myself and others are having around permitting reform, yeah, we really start out of the gate to say to the administration, if you want permitting reform, and your constituents certainly do, then let's start by following the law. Like there are huge, you can't issue stop work orders. There's a secretarial order from Secretary of the Interior, Doug Burgum, that has like 69 different very minor things that the regional BLM office just approves on their own, like a right of way here, a right of way there. That is just a stack of red tape on his desk now because he has made this morass of red tape so that these projects can't move forward. So one, we need our colleagues to figure out how we're going to get out of that box and actually know that when we pass permitting reform, that the administration is going to follow the laws that we pass. But I do think that this is a time when permitting reform could be real. Like we could get this across the finish line. Republicans want certainty. Renewables need certainty. And then we need to get back to believing in agencies like the Department of Energy to lead our way out of this and to fund that and to stop, chasing some of the brightest minds at the Department of Energy out of these programs because they really are the future of our country in many ways. And so I appreciate the opportunity to join all of you. I think if we put the effort into these high heat processes and the funding the way we have in generation over the course of the last 20 years, we can solve every single one of these problems. I just look at my own house. I turned off the gas to my house several years ago because everything I didn't require it anymore. And some of these high heat processes, we're going to find new ways to satisfy the exact same requirements. It's kind of like my friend Jigger Shaw says, people want, they want hot showers and cold beer. They don't know what energy is. And we need to take that kind of approach to the industrial sector because we need those processes. We need those factory jobs here in the US. And it doesn't really matter how we get there so long as we can do it at a reasonable price point and in a way that protects our future.
Well, thank you so much, Senator Heinrich and Senator Whitehouse. And you'll be happy to know that one of the examples we're going to walk through in detail is beer, electrifying beer as a process. And one of the heat pumps that is deployed already in the United States is in Colorado, where they are making beer with clean electricity rather than with dirty fossil fuels. And that's exactly the kind of thing that we want to see. And what our modeling shows is that even if electrification doubles the cost of energy as an input to beer production, it's 1 cent a beer. That's all it costs. So this is something that we can do. It's super important, and we really value you joining us today. So with that, I'm going to continue to share some slides and walk folks through the rest of the report. And I'm going to pass it over to my colleague, Eric Masanet, to really kick us off for the rest of the presentation.
Yeah, well, thanks, Leah, and thanks to Senators Whitehouse and Heinrich for the great context that you provided. So it's really now my pleasure to step you through some of the highlights of our report, which has just been released on our website and can be downloading using the QR code that you see here. So we'll give you a moment to take a snap of that. Go to the website, download the report. But while you're doing that and making sense of it, we're going to start by just giving you an overview of the challenge, the opportunity space, and the scope of our report. So, the US manufacturing sector, as we all know, produces a wide range of goods that we rely on every day. So, whether it's steel for our automobiles, or paper for our books, or milk and cheese for our refrigerators, one thing that most of those factories have in common is they all use a lot of heat, process heat, to convert raw materials into finished products. But as you see on this slide, not all of that heat is created equal. Around half of that heat is what we would classify as low to medium temperature process heat, meaning that it falls under around 300 degrees Celsius. Now, that might seem pretty hot by human standards, but by industry standards, it's actually quite low, considering that some industries like cement or iron and steel require process heat in the thousands of degrees in order to perform their operations. And so, why is this range of temperature important? It's because we have technologies that are available today that can replace fossil fuels for generating that heat with clean electricity. And these are ready today. So what this slide shows is just a selected summary of some of the electrified technologies that we have on the shelf today for some key sectors that use a lot of low and medium temperature process heat: food and beverage, chemicals, and forest products. These are the technologies that we're seeing deployments of today that are ready to go, and there are more coming down the pike, which will help us electrify even harder to electrify sources of heat in the future. And just to give you some context, the results you're going to be seeing are really focused on three primary sectors in the United States. Which are these sectors? These are the chemicals manufacturing sector, the pulp and paper manufacturing sector, and the food and beverage sector. So collectively, these three sectors account for many thousands of products that we purchase in our daily lives that are critical to our economy. They account for many jobs across many states in the United States, but they also account for the vast majority of that low and medium temperature process heat opportunity that we're going to be exploring today. Overall, all forms of heat in those sectors account for around a third of the emissions from the US manufacturing sector. And the US manufacturing sector is clearly only one of the sectors that we need to decarbonize, but it's an important one. But just to put it all into context, if those numbers seem a little small, we need to take a step back and remember that the US is the second largest emitter of greenhouse gas emissions globally, right after China. So this one space, low and medium temperature process heat in these three critical sectors actually can contribute an outsized share of the global mitigation we need to keep our global temperature rise in check. So they're very important. And with that, I'm going to pass it back over to Leah, who's going to talk a little bit more about our scope.
So what we do in this report, which, as I mentioned, was quite an undertaking, a very large team of engineers and policy analysts working for really a year and a half. And we wanted to answer this question, which is, where is it most technologically and economically feasible to electrify industrial process heat today? That's the question we want to answer. And what we focused on here is really four main technologies. So the first is an industrial electrode boiler. This is what we're going to call a sort of drop-in technology, because you could take a natural gas boiler that's already operating at a plant and you could replace it with a fairly similar footprint as well as a fairly similar process. And you can think of it as equivalent in, for example, the building sector to something like a resistance heating technology. The second big technology, you won't be surprised to hear me say, is a heat pump. It's an air source high temperature heat pump. So these are much bigger than the heat pumps that you might be familiar with in a home context, in a building context, but they have the same sort of principle. And there's been a lot of breakthroughs recently with companies like Atmos Zero and Skyven that are able to do higher and higher temperatures at a more economic price. But I don't want to leave aside other direct combustion that's happening. So right now, for example, if you want to cook something, like you're making cookies, for example, in a facility, or you're drying herbs for tea, dried tea, that is using direct fired gas in a lot of cases. And we can be swapping those out for electric ovens, just like you might have in your own home, an electric oven and an electric dryer, right? Same sort of principle, but on a really big scale. And so what we looked at for each sector is we came up with four scenarios that combine all these technologies. So in the baseline scenario, what we did was we first modeled the processes of how we think these plants are operating today across all these different subsectors. And then what we did is we said, well, what if instead of using gas boilers and instead of using gas ovens and dryers, you instead swapped in an electrode boiler? So that scenario is what we're calling drop-in electrification because it doesn't require a lot of systems change and it has a similar footprint in the actual facility. Now, you can also combine that drop-in electrification with energy efficiency upgrades. This is an old idea that is evergreen, right? Which is the idea that we could be insulating pipes, for example, using waste heat recovery, trying to maximize every little drop of heat throughout the system so that it's not leaking away. And so what we look here is at pretty tried and tested ideas for how we could upgrade the thermal energy efficiency of these plants. The second major block of scenarios is what we're calling an advanced electrification scenario. This is a scenario where we're swapping in an air source high temperature heat pump, and we're also electrifying those downstream processes where they exist, like those ovens and dryers. And again, we have a scenario where we combine that advanced electrification, putting in that heat pump, which might require, some retooling of the plant a little bit or a little bit of different floor space. That's why we're sort of framing it as advanced. And we combine that with energy efficiency too. And what you see here is combining a really efficient machine, a heat pump, very efficient, right? It has coefficients of performance of like 300%. Combining that with traditional energy efficiency is really where you get a lot of those operating cost savings because it's just such an efficient process. So with that, I'm going to pass it back to Eric to walk you through what this modeling process actually looks like in practice.
Thanks, Leah. And I promise I'll be concise here because what you're seeing is quite complex. And that's because industry can also be very complex. And so the way we designed this project is we didn't want to just make high-level assumptions about what a fluid milk plant could do or what a pulp and paper plant could do. We wanted to base our analysis in a really rigorous understanding of the operations that are occurring in those types of plants. And we did so by developing a series of what we're calling process archetypes. And the example you see here is for breweries, circling back to the idea of beer, which we'll get to also at the end. And the idea behind these archetypes is that we wanted to acknowledge the complexity of industrial plants, but also cut through that complexity so that we could identify opportunities that were both feasible in a real world context, but also realistic for plants. And so what you're seeing here is kind of a schematic of what an archetype looks like. So for making beer, there are a number of unit processes that occur in most breweries. These facilities use a lot of steam and hot water that typically comes from a boiler. And we've modeled all of the energy and mass flows that allow a facility like this to take in its inputs and to produce that output, so many liters of beer. The advantage to this is it makes sure that we get all of the process, intricacies correct, right? We don't ignore something that would be potentially a barrier in a real world plant. The archetypes are also open source, meaning that anyone can use the code, look at our assumptions, replicate it, and vet them right down to the specific technology. And here's how we use them. So this first baseline archetype, we start with this understanding, and we calibrate these archetypes using reported data for large breweries coming from, for example, the EPA's greenhouse gas registry, other information from the literature to make sure that our baseline understanding of a sector is technically accurate. We then use the archetypes to start deploying technologies. So Leah just mentioned, described to you, I should say, our scenarios. So in our first scenario, we're looking at electrifying the boiler, replacing the natural gas boiler in a typical brewery with an electrode boiler. And we're also electrifying the spent grain dryer that was previously running on natural gas. But we're doing so in a way that respects the overall energy and mass flows of the facility. Next slide, please. We can also use the archetypes to look at even more ambitious scenarios. Well, what if we didn't just go for electric boilers, but we considered deploying an air source heat pump? The big advantage to heat pumps as opposed to electrode boilers is that they're much more efficient for providing a unit of heat. Why is that? It's because they move heat from one place to another by using electricity rather than creating heat through either combustion or, a resistance coil. So you get a big efficiency gain by using air source high temperature heat pumps. So this was another scenario. And then finally, because we've modeled these plants with such detail, we can also look at the first fuel, which is energy efficiency. It's called the first fuel because often it's very cost effective and it allows you to save energy rather than investing in more energy in the first place. And because of this detail, we can look at a lot of efficiency upgrades at a typical plant, including things like process controls, improving insulation, improving steam traps, a lot of technical details. But we can also deploy a waste heat recovery heat pump, as you see in this diagram. And for breweries, that could mean taking some of the warm water that comes off the wort cooler and recycling that heat and upgrading it to provide hot air for the spent grain dryer, thereby reducing the need for electricity after we electrify. So the beauty of efficiency is you get the same product with a lot less energy input, which means the investment that you need to make in a heat pump or an electrode boiler or even a dryer gets more tractable because the capacities go down thanks to plant level efficiency. So our argument is we want to do it all at once. And I'll turn it over to Leah to talk about some of the results from this approach.
Yeah, so now that we've walked you through how we do it, what do we actually find? So what we're looking at here is compared to the baseline, where we still have all these gas boilers and gas dryers and ovens. And you can see in this sort of green bar, that's the baseline amount of emissions that we're looking at in a given year. But what if, for example, this year, all throughout the country, by magic, everybody adopted an electrode boiler and paired it with energy efficiency, or everybody adopted a heat pump and paired it with energy efficiency? Well, you can see that in the 2025 scenario. And what you can see here is that air source heat pumps with the grid as it is today are already going to be saving pollution in day one. With electrode boilers, again, the analogy here, if you're familiar with resistance heating, and for example, the Southeast has a lot of resistance heating in buildings, is they're not as efficient of a process, so they need to use a lot of kilowatt hours to make that heat. And so with the grid as it is today, there would be some short-term emissions increases. But what you'll see really clearly is that by 2030, assuming these grid model projections from KBM are correct, and assuming we're able to build all that clean electricity that Senator Whitehouse and Senator Heinrich were talking about needing to do, what we can see is that very quickly these technologies, whether it's an electrode boiler or a heat pump, they start to have really big paybacks when it comes to cutting pollution. And the brilliant thing about electrification, which you might be familiar with if you know about electric vehicles or heat pumps in buildings, is that they kind of get cleaner over time, right? These machines are as clean as the input fuel that you're putting into it, as clean as that kilowatt hour is, as clean as the electricity is. And as we clean up the electricity grid, these technologies essentially get cleaner. And you can see that very clearly here, that out by 2050, we have very, very little emissions coming from these actual technologies because the grid is so clean. We also just wanted to unpack this for today. Now, this is using 2023 data, so it's already a little bit old, but that's the most, recent data that we had available. But you can already see that even 2 years ago, if you put in an air source heat pump on average across the United States, these are these high temperature heat pumps at an industrial facility, on average, you're going to already start saving emissions. That isn't as much the case for an electrode boiler, but it is the case in many states, like in California and Washington and Vermont. And that's because those grids are already clean. And what will happen is that as the grid gets cleaner over time, all of these technologies will really be cutting pollution very easily. So it's a very similar story to what we know from electric vehicles, right? Sometimes people think, well, if I plug in my electric vehicle, is it actually dirty because the grid is running on coal? These technologies, especially the heat pumps, are so efficient that they don't have to use that many kilowatt hours. So even as the grid is still cleaning up, they're already saving pollution. The other thing that we wanted to do in this project is really look in detail at what are the different emission sources, what are the different fuel sources from the chemicals, pulp and paper, and food and beverage sectors. And what you can see here is that in the chemical sector, a lot of the fuel is natural gas. Now, we can't electrify all of that very easily because some of it is higher temperatures that we're not looking at in this low and medium temperature process heat. But you can see here that that really big blue bar at the top under the baseline, what it turns into essentially is that yellow bar, because you're moving the on-site combustion of gas into sort of what you might call scope 2, or I think it's scope 3 emissions, right? It's the off-site purchase of gas, of clean electricity. And so you can see here that it really does shrink down if we electrify the parts of the gas that can be electrified easily in low and medium temperature process heat for chemicals. In the pulp and paper sector, if you're familiar with this sector, you might know that there's a fair amount of biogenic byproducts. What does this mean? It means that we're in this to burn things like black liquor or wood chips, right? Waste products from making the pulp and paper products themselves. So we're really, again, looking at the slice here in blue for the gas, and we're turning it into this yellow slice, and you can see that it is shrinking again over time. And one of the findings from our report is that pulp and paper is a really big sector with a lot of opportunity just with electrifying that boiler, because these are really, really large plants from an emissions perspective, even if we only look at the fossil fuels. Food and beverage, by contrast, is a sector where most of that natural gas can be electrified. You can see that that blue bar shrinks down a lot. And again, the yellow is just the electricity scope 2 emissions. And so as the electricity grid gets cleaner, that will get better too. Now, of course, you might be wondering, with all this talk about data centers and some of the things that the senator said, that, wow, if we need more electricity for all these large factories, isn't that going to increase electricity demand? Yes, it will. But this is something that can be managed. And my personal view is that this is a really important thing that we have to electrify, right? We want to keep manufacturing in the United States. We want to have these good paying jobs, and we want them to be clean. And for all the reasons that Senator Whitehouse talked about with the carbon border adjustment mechanism, right? It's going to be a competitiveness issue as well, to make sure that we're not being left behind as Europe continues to invest in these kinds of technologies. What we did in this scenario is we looked at the bottom quartile, the 25% of the plants that have the best payback period, and we said, what if they all electrify tomorrow? What would that do to the grid? And so some of the best paybacks that we're generally seeing are in the Midwest, and so that's where we see a really big jump. Similarly, in New York, there's a really good payback period because the electricity price compared to the gas price is such that it's actually a very good state to work on electrification. Now, this isn't how electrification would actually proceed. California, in our model, has such high electricity prices that in this 25% cheapest scenario, nothing gets electrified. Well, we know in practice that California is very committed to electrification. They have the Indigo program, for example, and they want to move factories in this direction. So in practice, we likely would see a very different pattern, but this just gives you a sense that we are going to have new demand and load on the grid, which is why it's so important that we build clean electricity really fast and we interconnect it into the system quickly, and that we make good decisions when it comes to other large loads like data centers, because the industry does have to be electrified if we want to be keeping good paying and clean manufacturing jobs in the United States. And with that, I'm going to pass it back to Eric to talk through the economics of electrification.
All right, thanks, Leah. So Leah just described how electrification can reduce emissions, but key question is, well, what about costs, right? So what we're going to talk about first is our upfront costs. So we defined upfront cost as costs related to the capital investment you need to make in a heat pump or an electric dryer, installation costs, and of course, if there are costs associated with redesigning a plant, ancillary systems, we tried to take those into account as well. But what we need to acknowledge is every plant is different, right? Especially when it comes to energy prices, which can vary a lot depending on where a plant is located. But there are other differences too, like the capital cost for a particular piece of equipment might vary based on your plant layout, your suppliers, your location, and so forth. So to address all these variations, we constructed two cases, which I'll go through next. One, we called the optimistic case. This is kind of the ideal investment case. What does that look like? It means the baseline technology for natural gas, what you may install anyway, status quo, looks a little bit worse, right, in terms of its capital investment and its efficiencies, right? Whereas the electric technologies, we have a lower CapEx and the more optimistic assumptions about how much that'll cost, lower assumptions for installation costs and so forth. So like the rosiest case for electrification and the worst case for the baseline technology. That's what we're calling optimistic because the gap between the two is smaller. The inverse of that is the conservative case, where we used higher cost estimates for electrification and lower cost estimates for the baseline and so forth. You get the idea. But by doing so, we were able to then analyze what this investment would look like, at least simulate based on our best assumptions for all the plants we considered in our analyses. And what you see in the graph are box and whisker plots that give you a sense of that variation. Now, to interpret the graph, it's important to look at, first of all, that zero line. This is a graph that gives us the delta. So the change in investment costs compared to what you would expect if you were to invest in the status quo technologies. And that's the horizontal dotted line there, the baseline costs. And as we move from left to right, a few things emerge. The first is, in the optimistic case, for all scenarios, there are a lot of installations where upfront costs are lower or fairly similar to what you would do anyway in a replacement case with using natural gas-based technologies. And those costs increase as our scenarios get more ambitious, as we move from drop-in electrode boilers to including energy efficiency, to advanced heat pumps, with efficiency. Of course, upfront costs go up. The level of the investment goes up. But if you look at those green box and whisker plots, a key finding is that these changes don't have to cost much more, if they even cost more, than what we would do anyway. In our conservative case, the investments look a little bit more challenging using worst case assumptions. And for some plants, they're worse than others. But by doing it this way, we could go into the investment analysis with both eyes open and be very transparent about where opportunities are ready to be seized today and where some of the more challenging opportunities may exist across our sectors of focus. In all cases, though, the energy efficiency had a demonstrable effect on our overall emission savings. We also considered net present value, which is a metric that's used by many companies when evaluating a project investment. And ideally, what you want is a net present value, that the greatest net present value, or a net present value that's the least negative, represents the most beneficial investment. So in this graph, what you're seeing is an NPV analysis. Now, a key caveat is that we didn't consider the return on the investment, which would be all the stuff that you're producing, which you make money for in a plant. Rather, what we considered were the upfront CapEx costs associated with the investment, the installation costs, the maintenance costs over the lifespan of the technology, and then, of course, the fuel or electricity you need to run that equipment over its investment period. And what we can see here is that in both the conservative and optimistic cases, there are more investments required to seize electrification opportunities from an NPV perspective, but the proposition gets more and more attractive as the level of ambition rises, going from a simple drop-in solution to one that's very ambitious with energy efficiency. And in the optimistic case, the gap between the status quo and these investments starts to shrink. And where investments play out in terms of where they're most attractive really hinges on two key factors. The first is the so-called spark gap. That is the ratio of the price of electricity in a state to the price of natural gas for the same amount of delivered energy. So if we have, for example, a spark gap of 2, that means electricity is twice as expensive as natural gas in that location for the same amount of energy to run your processes. So the most attractive investments are currently, we found, in states where that spark gap is the lowest. The other factor is the operating temperature, right? It takes more energy to reach higher temperatures. So industries that have a larger share of their energy use in the lower end of the spectrum for low and medium temperature process heat, think, basic steam or hot water. For those sorts of factories and those sorts of industries, the investments are also attractive. And on the next slide, what you can see is if you read the report, you'll find our summary of payback period. So a payback period is essentially a simple metric that tells one, if I make an investment, how long before the savings from that investment will pay off that initial investment. And if you don't save more costs than the initial investment, you have no payback. But we found that there are many locations around the US where facilities we think can achieve payback periods today that are fairly low. Here you see in the graph, we considered 3 ranges of payback. Under 5 years, these are sort of the slam dunk investments, between 5 and 15 and greater than 15 years. And as we move up in the ambition levels across our scenarios, we're adding more and more facilities that have reasonable payback periods today. The distribution of these payback periods, as I mentioned, really relies on a couple of factors. Where the more attractive end of the distribution may be is a function of the spark gap, and then also the type of industry. So in our report, we've identified what we're calling hotspots. These are opportunities that we think are attractive today, depending on both their location. So you'll see states like Delaware and New York and Pennsylvania that have reasonably low spark gaps today. and types of industries, poultry, pulp and paper, dairy manufacturing, and so forth, which may have a good portion of their energy use that is related to the lower end of the temperature spectrum, meaning we can seize that opportunity through electrified technologies today and for substantial savings. And we also considered, beyond just greenhouse gas emission savings and the investment costs required, to seize those savings, we wanted to shine a really strong light on the co-benefits of moving to electrification. So in addition to looking at greenhouse gases, we also considered local air pollutants, including NOx and SOx and particulate matter, using models of local air pollutant distribution and affected communities, and found that in addition to reducing greenhouse gas emissions, between now and 2050, if we were to seize the electrification opportunity space, we would seize hundreds of billions of dollars in cumulative health benefits. We would avoid 1.1 million lost workdays due to respiratory illness. We would hopefully prevent 9 million asthma attacks and prevent nearly 3 million lost school days due to poor air quality if we can electrify the heat that we've identified. We'll also address the pollutants that lead to these, adverse outcomes. Avoiding these is another big reason for pursuing the electrification opportunities in our report. Back to you, Leah.
Yeah, so one of the things you might think looking at some of these cost findings is, wow, this is expensive. But that's actually not really true. So heat as an input to manufacturing processes is actually not a really big proportion of total costs. Let's take, for example, that gallon of milk that I mentioned earlier. If we were to double the cost of energy through electrification, which is a reasonable guesstimate given what we are looking at in our report, that would raise the cost of a gallon of milk by just 1 cent. Similarly, if we are looking at, for example, a 12-pack of toilet paper, again, if we doubled energy costs, it would raise that by 6 cents. If you bought a 6-pack of beer, it would be less than 1 cent per beer. So these are things that are very doable in terms of the total cost of producing these products. Now, I want to make sure we leave time for questions here, but in the report, we looked at a bunch of different policy scenarios for how we could begin to make more progress. Of course, companies can just take action today, and it's wonderful to see some examples of that. But we could also see government support at the state or federal level. We look at a baseline scenario of no support, and then we look at both capital CapEx investment policies, which are things like a 30% federal investment tax credit, or something like 100% of a grant that you might see at the state level. And then we looked at production support policies. This could be things like reducing the industrial electricity price by about 25% or reducing it by about half. And we also looked at policies like those that Senator Heinrich have championed around creating a clean heat production tax credit. And we looked at a scenario for $5 per MMBTU and a higher scenario of $10 per MMBTU. And then we also looked at a combined one where we take a CapEx ITC of 30% and we combine it with a reduced electricity price of 25%. So what does this look like? Well, as Eric already walked you through under this no policy scenario, we're looking at projects being in the money in something like 15% of cases across these different sectors. And they have relatively longer paybacks, even if they're in the money of, 15 plus years. But when we start to see policy, things like reducing the electricity price by 25% through a beneficial electrification rate. Many utilities offer rates for charging an EV that is a lower rate. We could also be doing that for clean factories that are using, for example, heat pumps. And when you can see is where we really start to have scenarios where a lot of these facilities are in the money is when industrial electricity rates fall by about half for a beneficial electrification rate, which is something that public utility commissions and state legislatures would have to take on if that were to happen. And if you have a federal production tax credit of that $10 per MMBTU. Both of those policies bring a lot of these projects into the money. This is a lot of stuff, and you can dig into this data in the report or online. But let's look at the Colorado Brewery, because that is a case where we already have an example of an electrification project. What you can see here is under no policy, we're looking at paybacks of, let's say, 20 years. But if the electricity rate goes down by 25%, by about a quarter, you get about a 7-year payback. If you have a capital CapEx support, like Colorado does have, they have a tax credit in place right now that they're working through for industrial electrification. That brings projects more like in the 15, 14-year range. And again, the production tax credit that Senator Heinrich has worked on, that really brings a huge amount of these projects into a payback period of around, let's say, 3 years. Across the states, there's different spark gaps and different processes. And so we model the sort of abatement curve. You probably are familiar with marginal abatement curves, and you can look at that if you're interested. There's some states like New York that really stand out in terms of making good progress. And we just also wanted to highlight that these are things that are already happening in the world. It's not just our report with theoretical ideas. There are real factories in the United States and also in other places like Europe that are doing this. So in the pulp and paper sector, we have examples of lumber drying in many states across the country. In upstate New York, we have an example of an ethanol production facility that's using a waste heat recovery heat pump. And the classic example in Colorado of New Belgium Brewing, all the climate people should buy their beer, I suppose. They are an example of using an air source high temperature heat pump. I just also want to mention that another way to deal with some of the higher operating costs is to think about other technologies that directly use heat rather than using electricity to make heat. So that is, for example, geothermal, and we've already published a report about how next generation geothermal can be used in the industrial sector. We're very excited about this work and think there's a lot of opportunity. And we also talk briefly about solar thermal as another example, and it is being used, for example, in milk processing plants already in California. So some of the policy recommendations that we talk through in the report are reducing risk and capital expenses by some of these upfront capital CapEx support policies, reducing operating costs overall, using things like efficiency and pollution standards as is being used in some air quality management districts in California. The example under the Biden administration of having buy clean programs from the federal government is something that states can do and that we should see again from the federal government in the future. Reducing and eliminating fossil fuel subsidies is very important, and creating technical assistance programs so that factories can learn from others that are already doing this and share best practices. Before I turn it over to questions from folks for the last 8 minutes or so, I just want to point out that one of the things we did is create a very dynamic web tool where all this data is live. And so if you want to know where are these factories in my community, or you're a campaigner working in a specific state, you can go and look up this data. You can see based on the size of these circles how big the pollution is from this facility, and you can play with different policies and see how that affects the costs and payback for those facilities. So we really encourage folks to check this out, particularly those doing active work on industrial electrification. And as Eric mentioned, so much of this work is open source. So we really do want to be in collaboration with folks. So with that, I'm going to stop sharing my screen. And I see that we have a couple questions here. Ron Steenblick asked a question about plastics and how do we want to, I'm going to just summarize it, do we want to continue to electrify plastics necessarily when they have all these other negative impacts for society? I just skimmed that question, so I hope I approximately hit the nail on the head. But Eric, do you want to try to take that one?
Sure, and I'll just be brief, and I hope the answer is not too unsatisfying, but it's a great question. We have to recognize that, the plastic sector is very heterogeneous, right? So there are, throwaway plastics that we should certainly try to reduce and eliminate that are ending up in our waterways or promote sort of, one-time consumption. But there are a lot of plastics that we do need for things like electronics and semiconductors and automotive materials and other applications, which are much harder to replace. So we didn't try to weigh in on the relative merits of different types in this project. We really just tried to show that plastics, like a lot of other aspects of the chemicals industry, is pretty prevalent in the US, and there are ways of decarbonizing whatever you produce from those facilities using the technologies that we considered. I think I'll leave it at that.
Great. And my apologies, Ron, if I didn't quite hit the nail on the head. I had to summarize the paragraph shortly. Another question from Ruth Chekhanoff. And apologies too if I'm butchering your names. I'm doing my best. So she asks, why did we choose to model air source heat pumps rather than ground source? Well, as I mentioned at the very end, probably after you asked this question, we did actually do a whole deep dive on geothermal, and that is an area where advanced technologies could really unlock a lot of heat that is directly at the site. So historically, geothermal was in these conventional sources where you would have a warm area, like think about Iceland, think about New Zealand. You have all this volcanic, geologic activity. Well, now with these next generation technologies, you can do them in a lot of different places. And so in that report, we talk about the opportunity for the industrial sector, and we're very excited about that. Tom Lingefelter asked, what is next for this work? So Eric, do you want to answer that one? What are we going to do next?
Yes. So in the coming weeks, if you keep in touch, we'll be releasing our full library of archetypes. So with any sort of open source code, there's a lot of, user instructions and sort of cleanup that goes into it. We'll be releasing our technology database. So what we're hoping to do in this project, besides just have very, focused analyses on our policy questions, we also want to help share information across the industrial modeling community, starting with sharing our archetypes and databases. And hopefully over time, more modelers will do the same, because the industrial sector, it's always been there, but we have just very poor data on this sector compared to transport or buildings or other things that we want to decarbonize. So it's in that spirit that we'll be releasing our data and archetypes, and hope people can use them and maybe share yours with us, and we can lift all boats together. What's coming next is we're going to be considering more technologies. So the question about why not consider water or ground source heat pumps is a really good one. We started with air source heat pumps because they're fairly complex, but our framework now allows us to change the input temperature from the heat source. And if that's water nearby or the earth constant 50F or whatever that is, we can now accommodate a lot of technologies based on the sort of calculation infrastructure we built up. So we're going to be expanding our list of technologies, looking at more detailed cost analyses, looking at more sectors, and hopefully taking part in a larger community of industrial modelers who will share models and data like we're trying to do here.
Great. And another question is about how do we deal with these longer term paybacks when companies often want 2 to 3 year paybacks? Yeah, so that's true. Companies often want a quick payback, but companies do things for a lot of different reasons, and they don't do things for a lot of different reasons too. I don't think that companies are not electrifying today because they think it's very expensive. They probably don't actually know how to do it because there aren't a lot of examples today. And so what we're trying to do is shine more light on the possibility here. And you could have companies who have, net zero targets, or who have a customer base that's mission aligned and that want to meet these kinds of goals and do it for that reason. You could also have purchasing programs. So for example, right now, when you make a book, you can get recycled paper, right? And that's a very common thing that environmental books want to buy that paper. There's actually kind of shortages in that. Well, what if we also created a kind of certification program for electrified paper production, right? What if we had the federal government or state procurement say that we're only buying clean products when we buy things? This is what was happening in the Inflation Reduction Act, with a lot of different parts of the federal government being first buyers for these clean products and sort of paying a premium for them. So there are ways that we can crack this nut, even if those paybacks aren't necessarily there. And the other thing I want to mention, as we talked about, is that even if you end up doubling your heat costs, it's not a big proportion of total production costs. So companies do all kinds of things. They spend money on marketing and distribution, right? The production has a lot of other inputs other than just heat. And so at the end of the day, even if it increases the costs, we're actually looking at pretty small impacts for a lot of these sectors in terms of the overall cost on the product. Richard Hart, our friend Richard Hart, has a question. Did your work lead to any recommendations on specific attributes of facilities that make them attractive for action? Why don't you take a crack at that one, Eric?
Wow, it's a really great question, Richard, and I'll try to be concise. But I would like to say, the type of analysis we did was a scoping exercise, right? We looked at the technical potential if all of these plants could electrify today, and we know they can't all do it today, right? The best ones that have a near-term opportunity are ones that are facing an equipment replacement soon, right? The boiler's getting old, the combustion units have been around for a while, they're getting ready to invest. Now's a great time for those facilities. Facilities that have more standalone boilers, meaning they're not generating steam through combined heat and power. We excluded that segment of the market because it's very tough to decarbonize. But low levels of heat integration, you've got a standalone boiler or dryer or dehydrator that needs to be replaced. The spark gap is clearly important. So if you're in a state that has a small spark gap rather than a large one, electrification is likely to be beneficial. If you're operating at temperatures that are amenable to the temperatures that can be reached by the technologies we looked at, meaning lower end or medium end of the spectrum. And of course, you've got to have the interconnect, right? So if you're in a very power stressed, grid stressed region, electrification might be more of a near-term challenge to you. But if you're not, and you can check all those boxes, those are the facilities that are prime for very near-term electrification following the recommendations in our report. And I'd just like to remind, the users of our report that we've tried to lay out, what's at stake. If we can seize all these opportunities, how much will we save? By how much will we reduce health impacts and emissions, right? But a key next step is identifying those facilities that can be electrified today versus the one tomorrow and then the day after that. That's where the real work has to begin. And I would say those are the key factors that would be the make for a facility that could be, towards the, closer to today than to tomorrow.
So I know others had more questions. Feel free to follow up with us on email, and we're happy to have continuous conversations. I just want to close by saying that many of the folks who came today are advocates who are out there working on industrial electrification. Others are folks working at companies doing the good work of industrial electrification. And we just want to say that we are so grateful for all of you and the work that you're doing, not just for the fact that you came to our webinar today, that's nice, but really the work that you are doing to forge a new path and create a model of the sort of future that we need. And so we really want this work to be in partnership with all of you, and we're so grateful for everything that you're doing. With that, I'll give Eric the last word.
Yeah, well, thank you everyone for coming. And I'll just echo that a lot of the inputs and insights that we had that shaped our results came from those very projects, those very innovations, those very startup companies that are innovating on the heat side. So please keep up the good work and thank you for all of that. And know that it does make a difference, even in reports like ours that are shining a light on the opportunity space. So with that, please do stay in touch. Please do reach out if you have questions. Download the report. Stay in touch because we'll be releasing more data products, and we really appreciate you spending an hour with us today to share our work.
Thanks so much, friends. Have a lovely holiday season wherever you are. We appreciate you. Bye.
Bye.